All right, so in the last video we introduced the environment we're operating in Part D. We're considering goods that are almost entirely non-excludable. And to do this means we have to take a step away from the models we've been developing in Part B and C, which we call markets. In Part D, we're going to actually introduce a new type of tool set, what we call game theory. And these are just sort of the basics. So if you have more interest in these things, there's a lot more to explore. Okay, so let's just introduce three definitions before we start playing some actual games and using these ideas in practice. So the first definition is what we call a best response, which is a strategy that gives a player the highest payoff possible given the strategies chosen by the other players in the games. So we'll talk about what a strategy looks like in practice. But sort of at a high level, a strategy is just a way of playing a game. So a best response is telling us how we should play in response to every strategy of a rival. And then the second definition is a dominant strategy, which is a type of best response where it doesn't matter what the other player is doing. So no matter what the other player is doing, we know what we should do. So an example of not a dominant strategy is if the weather is sunny, I should not wear a coat. But if the weather is cold and rainy, then I definitely should wear a coat. So depending on what the weather is, I should do different things. A dominant strategy tells us that when our rival no matter what our rival does, we should do exactly the same thing. And then the last definition is a Nash equilibrium, which is essentially a pair of strategies where no player wishes to change on their own. So there's sort of fancy terminology for this, but the way we call this unilaterally changing a strategy. This just means a one-sided change. So when we've talked about markets, we've talked about the logic of where equilibrium comes from. And you'll remember, we talked through buyers and sellers wishing to move their prices towards some P star, the equilibrium price. And this price, we talked about both buyers and sellers having no incentive to change the price they're selling and buying. This idea of a market equilibrium is actually a type of Nash equilibrium. Neither buyer nor seller wishes to change the price they're buying and selling. And this is the core idea in a Nash equilibrium. So let's make this more concrete. So this is an example of a game matrix. So we have payoffs represented in the matrix, and then we have two players, and both players can play one of two things. They can either choose to cooperate or defect. So for player one, we have one strategy, cooperate, and another strategy, defect. And then player two also has two strategies, cooperate or defect. And then in the matrix, we have represented these different numbers. And we're going to walk through what each one of these numbers represents. So if player one chooses to cooperate and player two also chooses to cooperate, then player one gets a payoff of 3, represented by the first entry, and player two gets a payoff of 3, represented by the second entry. So the first one corresponds with player one, it's the first one, and player two's payoff is the second. Which is just sort of handy notation. But then if player one chooses to cooperate and player two chooses to defect against them, player one is playing nice, player two is playing mean, player one gets screwed over. So they get a payoff of 0, and player two gets a very high payoff. So player two is playing mean against player one is trying to cooperate, and player two refuses. They defect against them. So in this case, player two gets a huge benefit. So instead of getting 3, they get a payoff of 5. So player 2 has some incentive to switch from cooperate to defect and go from a payoff of 3 to a payoff of 5. So in this entry in the matrix, player 1 is defecting and player 2 is cooperating. So this is sort of the flip side of the last entry. So if player 1 chooses to defect against player 2 choosing to cooperate, player 2 is playing nice, player 1 is playing mean, and player 1 gets a huge benefit from that, screwing over player 2. So player 1 gets a payoff of 5, which is definitely better than their 3. And player 2 gets a payoff of 0, which is worse than their payoff of 3, if they both cooperate. But then lastly, if they both defect against each other, they're both playing mean against each other, this is sort of bad for both of them. They both get a payoff of 1, where if they were to cooperate with each other, they would get a payoff of 3 and 3. So let's think about how we might play this game. We have a very systematic way of solving for this type of game. How we would follow our individual incentives as given by this payoff matrix. So these numbers, as we talked about on day 1, the numbers simply represent rankings. So I like a higher number more than a lower number. These numbers just correspond to the things I like better and worse. So we're just going to walk through this systematically and think about the incentives of both player 1 and player 2. And then think about how we might arrive at an equilibrium very similar to what we discussed in part B with market equilibrium. All right, so what we'll do first is isolate the strategy of player 2. So we'll look at one of the two strategies and think about what player 1 should do in that case. So let's say player 2 chooses to cooperate. What should player 1 do in this case? Well, if player 2 is cooperating, player 1 is given the choice between cooperating and getting a payoff of 3 or defecting and getting a payoff of 5. So higher numbers representing higher preferences, player 1 should choose to defect. So if player 2 is choosing to cooperate, player 1 is choosing to defect. So we'll put a box around their payoff. So we have pink representing the best response for player 1. And in this case, if player 2 chooses to cooperate, player 1 should defect. Now, to do this systematically, we have to look at every possibility of the game for player 1. So we've just looked at cooperate, but we also need to look at defect. So if player 2 is choosing to defect, this isn't as good for player 1, but we still need to make a choice between cooperating and defecting. So if player 2 is choosing to defect, player 1, if they cooperate, gets a payoff of 0. And if player 1 chooses to defect, then if player 1 chooses to defect, player 1 gets a payoff of 1. So 1 is better than 0, so we'll put a box around this. Okay, so this is amazing already. What we've done is identify the best response for player 1. In every possible state of the world, every possible choice of our rival, we've defined what we should do. If player 2 chooses to cooperate, we should choose to defect. And if player 2 chooses to defect, we should also choose to defect. So this is our best response, the thing we've boxed in the matrix. But you may notice what we do doesn't depend on what player 2 does. If player 2 chooses to cooperate, we should defect. If player 2 chooses to defect, we should also defect. So you'll remember our definition of a dominant strategy. Our best action doesn't depend on what the other player is doing. In this environment, in this game, player 1 has a dominant strategy of defecting. Okay, so we've thought about player 1, let's think about player 2. So what we do for player 2 is just exactly what we did for player 1, just sort of flipping the matrix. So we look at every possibility of player 1, and then we ask player 2 what they would wish to do. So if player 1 is cooperating, player 2 is given a choice between cooperating and getting a payoff of 3, or defecting and getting a payoff of 5. Remember, the entries in the matrix represent the payoff of player 1 and the payoff of player 2. So player 2 is given a choice between cooperating and defecting. And because 5 is greater than 3, then we would choose to defect. So we'll put a blue box around their payoff that corresponds with their best response in this state of the world. Okay, so if player 1, on the other hand, instead of cooperating, chooses to defect, then player 2 is given a choice between cooperating and getting a payoff of 0, and defecting and getting a payoff of 1. So in this case, if player 1 is defecting, player 2 should also defect. So we'll put a box around player 2. Player 2's best response in that state of the world. So here, again, amazingly, what we've done is define player 2's best response. No matter how the game is played, we know what we should do. We've put a box around these things. And just like for player 1, our best response is also a dominant strategy, because no matter what player 1 is doing, player 2 should defect. Okay, so how should we play this game? What are the points in this game, the pairs of strategies, where neither player wishes to change on their own? In other words, what's the Nash equilibrium? What's the equilibrium point, just like we found with prices and quantities in markets? What's the point where neither player wishes to change? Well, we can easily find this simply by looking at the matrix and identifying the boxes, the points in the matrix, where both payoffs are boxed. Remember what the boxes tell us. It's at this point that the player does not wish to change. So if we identify entries in the matrix where both payoffs are boxed, that tells us this is a point where neither player wishes to change. They're actually playing what they would wish. So in this case, we have a Nash equilibrium of defect. I've put a box around the entry in the matrix, but the way we would actually write this is that player 1 chooses to defect and player 2 chooses to defect. We don't actually write the payoffs as the Nash equilibrium. You'll see this in some of the examples we work through later. So I've put a red box around the Nash equilibrium, but you may have noticed that this entry here is not the highest payoff for the two players. 1-1 is actually worse off for both of them than cooperate. Defect, the Nash equilibrium is worse off than cooperate. If both players were to cooperate, then they would get 3-3. But if they were to play their dominant strategies, they would get 1-1. So what this means is that player 1 and player 2, following their individual incentives, pushes this game towards a suboptimal outcome. We have our socially efficient outcome and our incentive outcome, our Nash equilibrium. And these two things do not match. This intuition should work very closely with your intuition for the solutions we came up with in part C. When we have externalities, markets on their own do not maximize the welfare of society. In this game, we've also shown a similar result, that following your individual incentives does not lead us towards a socially efficient outcome. Okay, so let's play another game. So let's say you're planning a date and you've forgotten your date's phone number. You've lost it, you lost your phone, you have no way of communicating. But you know something about each other's preferences. You know, you both want to go on a date together, and you know what each other likes to do on a date. So there are two options. One, you can go to a play. The other, you can go to a movie. You have no way of communicating. You just know that you like to go to the same place, and you each have slightly different preferences for plays and movies. So we're going to play this game. We're going to figure out if there's a way of knowing what you should do beforehand, and we'll talk about Nash Equilibrium of this game. Okay, so let's say you're player 1 to start with, and let's identify what player 2 is doing. So we're going to run through both states of the world, just like we did in the previous game, and we're going to try to find what the individual incentives will tell us. I might warn you, the conclusion of this story is a little bit more complicated than the previous one. All right, so first off, we're going to identify that player 2 is choosing to go to the play. So what if your date is going to the play? What should you do in that case? Well, if you go to the play, you get a payoff of 2. If you go to the movie, you get a payoff of 0 because you're not matching them. And so this is worse off for you. So the best thing for you to do is to match your date and go to the play with them. Okay? And then we're going to look at the other possibility. So what if your date is going to the movie? What should you do in that case? Well, just like before, we want to match our date. So if you go to the play and they go to the movie, you get a payoff of 0. Turns out they do too. And you get a payoff of 1. You get a payoff of 1 if you go to the movie with them. So in this case, you should go to the movie. Again, you should match your date. Okay, so this is a best response, which we've identified in the payoff matrix, and it's not a dominant strategy. We know what we should do in both states of the world, but depending on the state of the world, we should actually do something different. So we should match play and match movie. So let's flip this. Let's think from the perspective of player 2 now. And we're going to use this systematic approach. So if player 1 is going to the play, then what should you do as player 2? Well, just like for player 1, you want to match the action of the other player. So we have going to the play as a payoff of 1 and going to the movie as a payoff of 0. So in this case, if your date is going to the play, you should go to the play. And then if your date is going to the movie, again, you should go to the movie. So this tells us that we have, for player 2, a best response that's also not a dominant strategy. What player 2 does should depend on what player 1 does. Okay, but you may have noticed that there are 2 entries in this matrix with both payoffs boxed. So it turns out in this game, there are 2 Nash Equilibrium. If your date is going to the play and you go to the play, you have no incentive to switch. You're happy you're both there, and so is your date. And so neither of you wishes to switch. This is a Nash Equilibrium because neither of you has any incentive to unilaterally deviate, to switch on your own. And the same is true with a movie. If it turned out instead that both of you are going to the movie, neither of you have any incentive to switch and go to the play instead. You're both happy that you're both there together. Okay, so it turns out here there's not a great conclusion for how to know where to go, either the play or the movie, based on your incentives. But you're going to see an example later where knowing something about the preferences of your date can give you some extra insight into which play or movie to go to. Okay, so let's play another game. Let's say we've switched the preferences around a little bit. So again, we have a play and a movie, but we've changed the preferences. So we both like going to the same place. It's good when we are in the same location. But it turns out, I as player 1, I like going to the play a lot. If I go to the movie, if I go to the play, I get a payoff of 1, even if my date isn't there. So if my date is going to the movie, I get a payoff of 1, because I love going to the play. If I go to the movie alone, it doesn't do anything for me. I don't really enjoy the movies. But if I go with my date, then that's extra nice. So I'm happy going to the movies with my date, but I don't really like going to the movies by myself. And then for player 2, if player 2 is going to the play, that's really nice for them. They, like going to the play. And they like going to the play, player 2, even on their own. So here we're saying if player 1 is going to the movie and player 2 is going to the play, then player 1 gets a payoff of 1. So they, it's not quite as nice if they go to the play with their date, but they're still happy going to the play on their own. If player 2 goes to the movie and player 1 goes to the play, this doesn't do anything for player 2. They get a payoff of 0. But if it turns out their date shows up with them, this is reasonably nice. So they get a payoff of 1. So both players like going to the play more than the movie, but both players like going to the movie with their date. All right, so let's approach this systematically like we have in the past. So let's isolate the first action of player 2. So we're saying player 2 is going to the play. What should player 1 do? Well, if player 1 goes to the play, then they get a payoff of 2. And if player 1 goes to the movie, then they get a payoff of 0. So we'll put a box around player 1's best response in this case, which is to go to the play. Now, if player 2 goes to the movie, player 1 gets a payoff of 1 if they go to the play, and they get a payoff of 1 also if they go to the movie. So here, neither one is greater than the other. So what we're going to do is actually put a box around both of them. So we've identified the best response for player 2 or player 1 in purple, which in some cases tells us what we should do. So in the case of the play, we know what we should do: go to the play. But when there's a movie, when our date is going to the movie, we're actually indifferent between going to the play and going to the movie, which is a little bit funny. Okay, so we're going to think from the perspective of player 2 now. We isolate one of the states of the world for player 2. If player 1 is choosing to go to the play, what should player 2 do? Well, just like for player 1, player 2 should go to the play if player 1 is going to the play. It's really nice to go to the play, and it's nice to go with your date. And then if player 1 is going to the movie, player 2 is given a choice between 1 and 1. And so again, just like for player 1, there's really no incentive to go either direction. Okay, so in this case, we have two Nash equilibrium. We have one that's in the lower corner, which is 1-1. Both players going to the movie, both of them could take it or leave it. They could go to the movie and they'd be happy going to the movie with their date, but they would equally likely or equally willingly go to the play on their own and leave their date at the movie. Sort of weird preferences. But this is a Nash equilibrium because there's no incentive to switch. It's either 1 or 1. So this is what we call weak preferences. So we're indifferent between going to the movie and going to the play. But when we look at play, in this case, both players have no incentive to switch. So if player 1 were to switch from play to movie, they would lose payoff. So we'd go from 2 to 0. So this is what we call a strict preference. We definitely like going to the play more than we like going to the movie. And the same is true for player 2. So this Nash equilibrium is much stronger in some sense. Here, it's like, well, I don't have any real reason to switch. but I'm not super drawn to going to the movie as opposed to the play with my date. Where here, this is the best thing for us. Neither player is even at all willing to switch. And it turns out this also corresponds with, the second Nash equilibrium corresponds with the socially efficient outcome. Both players choosing to go to the play is actually best for both players and for the pair of them as a whole. All right, so let's play one more game and then we'll wrap this up. So we've moved around the payoffs a little bit further. So if player 2 is going to the play, and player 1 goes to the play, this is very nice. But we have this weird thing where maybe they actually don't really like each other. Turns out they've gone on a bunch of dates. It's not that nice. And they would sort of wish to go different directions. So if player 2 is going to the play, player 1 goes to the play, player 1, likes going to the play, and will receive a payoff of 1. But, if they were to go to the movie instead, they would actually get a higher payoff. So if player 2 is going to the play, player 1 would sort of, wish to switch and go to the movie instead. So let's formalize this. Player 2 choosing to go to the play, player 1 would wish to go to the movies. But thinking from the perspective of player 2 going to the movies, what should player 1 do? Well, in this case, again, player 1 likes to go to the movies with their date, but they would much prefer to go to the movie, go to the play if player 2 is going to the movies. So they're wishing to switch away from going to the movies with player 2. So they sort of don't want to go on this date. So we'll put a box around this payoff. A payoff of 2. So here we have a best response for player 1, which is not a dominant strategy. Okay, so let's think about player 2 for a second. If player 1 is choosing to go to the play, what should player 2 do? Well, if player 1 is going to the play and player 2 goes with him, they get a payoff of 0. So this is very unnice for player 2. Instead, if they were to switch to going to the movies, they would get a payoff of 1. So player 2, if player 1 is going to the movies, player 2 would wish to go to, if player 1 is going to the play, player 2 would wish to go to the movies. Okay, so if player 1 is going to the movies, what should player 2 do? Well, player 2 going to the play would get a payoff of 1, and going to the movies with player 1 would give them a payoff of 1. So in both cases, they have an equal payoff of 1. So we'll put a box around both, and this is the best response for player 2. Okay, so this is what our best responses look like, and we can easily identify our Nash equilibrium by finding the areas in the matrix which have boxes around both players' payoffs. And that looks like this. So we've identified 2 of them. And both Nash equilibrium are actually the players going to opposite places on their date. So they don't really like each other, and they can't communicate. And so what they would wish is to go to different places. Our 2 Nash equilibrium are play movie and movie play. All right, so you're going to see a couple examples of this, how this relates to common resources and public goods. This type of approach gives us a lot of traction on goods that are non-excludable, both common resources, which are rival, and public goods, which are not rival. And we'll see some other examples of this type of modeling approach in the future. All right, I'll see you in the next one.